If you recall, last week, we wanted to talk about, I don't know if you wanted to talk about it, but I certainly wanted to talk about it. This arc length problem. I wanted to find the distance from the point 0, 0 to the point 39, but along a path other than the shortest distance. So I wanted not only the distance from 0 to 0 to 39 along this linear path, but also along this parabolic path. All right, also along that path. And we wanted to use the way we calculated the distance on the line segment, and we wanted to apply that to how we calculate the distance along the parabola. We're going to apply the same kind of thinking that we did back for derivatives and integrals when we found the slope of the line tangent. We couldn't find a slope with just one point, so we found a slope using 2 points, the point that we're interested in and a point nearby. Then we did the calculus thing and say, what happens if I take that point nearby and make it infinitely close to the point that I care about? The same thing happened with integration. We want to find area using length times width, but the stupid length was all continuously variable. So we flattened out the function in short bursts so that we could use length times width. We assumed that the function was constant for some small change in x called delta x, so that I could calculate using length times width. I calculated the value of the function at a certain point for the length, the delta x for the width, and then I just added all those up. We are going to apply the same thinking to this problem. So we know we can calculate the distance between 2 points along a straight line. And what we're going to do is approximate the distance from 0, 0 to 39 along this curve with a bunch of straight lines. So we're going to approximate the curve with line segments. So we'll start off at 0, 0. We'll go to the point 1, 1, then to the point 2, 4, and then to the point 3, 9. So we just connect with line segments. So here we broke this up into 3 line segments. And so what we calculate is the distance. I'll call this, let's see, this will be the third one. So we'll call this D3. Now we'll go 9 minus 4, or sorry, let's go 3 minus 2, so delta x and delta y. That's how much the x has changed. And then the y is 9 minus 4. Then the distance from 1, 1 to 2, 4, we'll call that D2. And the change in the x's is 2 minus 1. And the change in y is 4 minus 1. And then we'll have this first one from 0, 0 to 1, 1. That'll be D1. You know, it's the square root of 2, but we're going to write it out anyway. 1 minus 0 squared and 1 minus 0 squared. Then our approximation for this distance will be D1 plus D2 plus D3. Now, this is just going to be an approximation of the distance. At this point, we should have a side thought. Is this an overestimate or an underestimate? And more importantly, how can we tell? If you've been paying attention this semester, you know that this is the question that I will not be answering today. I want you to think about this approximation. Is it an overestimate or an underestimate? How can we tell? That is, as we add more line segments to get our actual distance, are we coming at the actual distance from below, or are we coming from above? Are we having an overestimate that we are dropping down to the actual value, or are we having a lower estimate that we're heading up to the actual value? That should just be running in the background. Our approximate length is just the length of these three segments. Because this is calculus, we know where this is heading. We improve the approximation by using more segments. Then we do the calculus thing, use an infinite number of segments. What happens as the segments get infinitely close together? That's the calculus way. We approximate, and we figure out how we're going to improve our approximation, and then just do that infinitely many times. To see how this is going to work, we're going to need to do a little bit of algebra. We're going to have to go back to our distance formula and think about how we can manipulate this. Because I wrote it on the board last week and I didn't erase it, and no one came in to erase the board. I guess it looked important enough. People are going, whoa, I better not erase this. But for those of you at home who cannot see the board behind me, what we're going to do is just take a closer look at the distance formula and see what the parts are. So let's take a closer look at what we're doing to make these calculations with the straight lines, or the line segments. So here's how the line segments work. I've got 2 points. I've got an x1, y1, and I've got a point x2, y2. And between them, I have some distance. The calculation is the square root of x2 minus x1 squared plus y2 minus y1 squared. X2 minus x1 is just the horizontal distance between the 2 points. We're trying to calculate distance at an angle, and it's made up of 2 distances. The horizontal distance, x2 minus x1, and the vertical distance, y2 minus y1. So we're going to abbreviate these 2 distances. x2 minus x1 is just how much x is changing between x1 and x2. So we're going to call that delta x. y2 minus y1, that's just the change in y. That's going to be delta y. So I'm going to go back to my distance formula, and I'm going to rewrite with the delta x and the delta y. So it's going to be the square root of delta x squared and delta y squared. Now we have to do the weird stuff. Now this is the point where we have to come in and decide and have to actually know what we're looking for to make stuff happen, at least algebraic. So this is not, the next thing that we're going to do is not something that you should have realized. This is something that only works because I know where this is headed. You know what I mean? It's really bad storytelling. It's like the hero is going to do this because that's what moves the story forward, right? Why does Bilbo leave the Shire? What was Bilbo's motivation for leaving the Shire? If your silence means he didn't have one, that is correct. The only reason that he left was that's how the story moves forward. Someone, Tolkien was really in a corner. He's like, oh, well, shit. Bilbo just goes. He's like, oh, but why though? He's like, oh, I don't know. He just does. If he doesn't, then the story doesn't happen. You know what I mean? Why does Luke go with Obi-Wan? Because stormtroopers barbecued his aunt and uncle. Spoiler alert. By the way, that movie came out in 1977. You don't get to have spoilers. You're like, well, oh, I haven't seen Star Wars yet. So anyway, what were we talking about? Oh, yes. So at this point, stuff is going to happen. And the only reason that stuff's happening is because I know where things need to go. It's really hard to spot otherwise. So at this point, the DM says, here's what's happening. And all the characters are like, oh, well, I guess we're going on the adventure, aren't we? And the DM's like, oh, yes, yes, you are. So choo choo, we get up on the railroad. And here's what we're going to do. I'm going to factor out the delta x squared. That's the weird thing that I'm asking you to do. So the weird thing that we're going to do is factor out delta x squared. So what's going to look like I'm going to take the delta x squared out of the delta x squared. I'm going to divide through by delta x squared. That's going to factor it out. That's going to leave us a 1 here. My delta y squared will have to get divided by a delta x squared. And then out here will be a delta x squared. Also, I guess my parentheses should be bigger. But that's what happens. Previous steps, like, well, what are we going to do with this? Then the next step is Bilbo running after the dwarves. Wait, I'm coming with. I factored out the delta x squared. Right now, we just need to see how this works. Mechanically, is everybody cool with this? It's weird because in your history of factoring, you're always factoring with integers. You're like, oh, 5 and 7 don't have anything in common. I can't factor anything out. You can absolutely factor out with a 5 and a 7. You can factor out whatever you want. You can factor the 7 out, and it's 5/7 plus 1. Or you can factor 5 out, and it's 1 plus 7/5. You can factor a 12 out, and it's 12 times 5 12s plus 7 12s. You can factor anything you want. You just got to divide all the stuff inside. If we multiply through by delta x squared times the 1 is the delta x squared. Delta x squared times delta y squared over delta x squared. The delta x squared will cancel out and leave a delta y squared. Nothing up my sleeves. Bilbo has left a shot. Here's what we're going to do next. Notice that I pointed over at the screen like you could see it. Notice that over here, I've got the square root of the delta x squared, and that we can simplify. So I've got the square root of 1 plus delta y and delta x are both being squared, so I can write that in one fraction. And then delta x squared, we can simplify to a delta x. Now it's outside of the radical. This is the distance between any of these 2 points. X1, y1, and x2, y2. Now we're going to apply some calculus thinking. We are going to make these points get infinitely close together. The delta x is going to get infinitely small, which means that the delta y is going to get infinitely small. And as the deltas get infinitely small, the delta x becomes the dx, delta y over delta x becomes dy over dx, which is just the derivative. So as the deltas get very small, as the points get infinitely close together, we stop calling them delta x and delta y, and we start using the infinitesimal dx and dy. So the delta x becomes the infinitesimal dx, and the delta y over the delta x becomes the infinitesimal dy over dx. So for points that are infinitely close together, that delta y over delta x is just going to be dy over dx, which is just the derivative of y with respect to x. Which is just the derivative of our function. This is super sketchy notation. Then what we're going to do is we're going to add up all these lengths, because that's all we're ever doing with integration. Integration is multiplication, but one of the factors is continuously variable. So integration becomes addition. Integration in this case will be this addition, d1 plus d2 plus d3, turn into d1 plus d2 all the way out to d infinity. Although we're going to have to go from, when we get to d infinity, there's nowhere to put the pluses anymore because we have a continuum. And then calculus says, just go over into the continuum part and it'll work out. So the arc length, we're just going to add up all these square roots of 1 plus f prime of x squareds times delta x. And then we'll just do this an infinite number of times. So this is the length of each line segment. Here we are adding up all the line segments. Here we are letting the number of line segments go to infinity. That's what integrals represent. Integration is just addition, because integration is multiplication, but one of our factors is continuously variable. Here, integration is just showing up as addition. Makes it a little bit different than our multiplication, but one of the factors is variable. This is a sigma, yeah. It's kind of a lazy sigma. I didn't put a little serif on. Now here, that's an N. So our A to B are just all the values of X for which we're making this calculation. So we're going to integrate from 0 to 3. Our function is y equals x squared, or f of x equals x squared. So f prime of x is 2x. And we just drop that into our arc length formula. The integral from 0 to 3 of the square root of 1 plus the square of 2x dx. This leads to the integral from 0 to 3 of the square root of 1 plus 4x squared, which is not an integral that we know how to do. So this is not an integral that we know how to do yet. But fortunately for our heroes, we can get an approximation. So we'll just go math, calculate an f an integral. We want to integrate the square roots of 1 plus 4x squared with respect to x from 0 to 3. So 9.747. We pulled out some fancy 90s technology for this one, but there it is. So 9.747. At this point, we'd be able to compare our original D1 plus D2 plus D3 and just see if that's an overestimate or an underestimate. So we can see if we are correct when we try to figure out if it was an overestimate or an underestimate. But now that we know what the answer is, we can go back and think, why was that the case? Why was our original D1 plus D2 plus D3 an over or underestimate? Any questions? How's everybody okay? Now, we got to think about what we care about from this problem. Too often, the focus becomes on the arc length formula, with the implication being that I want you to remember the arc length formula. One level up from that might be thinking that you want me to that I want you to understand or remember the derivation of the arc length formula, this delta x and the delta y, and then explain why Bilbo went on the adventure. But that's not it at all. The important thing here was that we took something that we already knew, how to find the length of a segment, and adapted it to a new problem. Because in math, that is all we ever do. Take what we know and adapt it to a new problem. We think about area. Area is equal to length times width. All of the extra area formulas that you carry around with you, pi r squared, 1/2 base times height. The average of the bases times the height, 1/2 b1 plus b2 times h. All those things you carry around with you are variations on length times width. They're shortcuts. That would be just remembering arc length formula, but not really understand what we mean by area, what we want to calculate. All of it comes from taking what we know and adapting it to something new. That's the goal. Does that make sense? That is the math. And this is the calculus way. Here's how you can approximate. Do that approximation infinite number of times. Or whatever you do to improve the approximation, just keep doing that, look for a limit. That's the thinking that goes along with it. That's the calculus way. Any questions? Is everybody okay? All right. The last thing that you have to do is a bunch of problems that I'm going to cobble together and label as being the final exam. So I'm going to put them up in the quiz module up on the Canvas. You're going to do all those problems. They will be due on December 16th, which is Friday of finals week. The homework is all due on December 9th, which is the Friday before finals week. So homework gets cut off at December 9th. So when you email me on December 10th, or you wake up on December 10th and say, I better get started on the homework, you are already done with the homework, because all the homework is over at that point, and all you have left to do are the quizzes. The quizzes cobbled together will form our final exam and all the tests in the middle. So just do those problems, and then you'll be done with this class. Any questions? Comments? Yeah, it's less scary if I call them quizzes. If I start labeling shit final exams, people start freaking out. So I like knock it down a peg. I used to give quizzes in class on paper, but then I'm like, oh, why do we use paper? Let's stop using paper. I'm making a ton of copies and it's ridiculous. And then I have to hand the paper back and collect the paper. And then I used to label them as quizzes, and people are like, oh no, it's a quiz. So and even though on quizzes, you're allowed to help each other out. You're expected to help each other out. If you turned in your quiz and then left, and like other people didn't do well on the quiz, I just gave you their score. It's like, oh, dude, we have to help each other out. That's like the whole point. I actually didn't do that, but I always toyed with the idea of giving students the score that you got plus the lowest score on the quiz. So it would be in your interests to do that, to help the other students out. But then it was a little bit too capitalism for my tastes, because you wouldn't be helping people for the right reasons. You know what I mean? Like if you don't do murders because you're worried about getting caught, that's still shitty, right? You shouldn't do murders because you shouldn't kill people, right? You shouldn't even want to do that in the first place. You know what I mean? It's not the law that keeps me from murdering people. It's morality that keeps me from murdering people. But anyway, that's all beside the point. I stopped calling them quizzes. I started calling them classwork. I just put at the top classwork. And then students were like, oh, it's just classwork. I'm calm and I can help each other. We can help each other out now. All right, that's going to do it for today. I'll see y'all on tomorrow. We will talk more about more problems. Everybody have a good day and thanks for playing.
Bye, have a nice day. See you tomorrow.
See you tomorrow.